Radiation protection, Part 17A, designing for radiation protection. We're going to talk about equipment regulations, design of protective barriers, radiation detection and measurement, and finally handling and disposal of radioactive material. For equipment regulations, there are two types. There are radiographic equipment and then those for fluoroscopic equipment. Radiographic equipment. So number one, we have the radiographic X-ray tube housing. The housing is 1.5 millimeters of lead equivalency. Its purpose is to absorb leakage radiation, which is leakage emitted anywhere but the tube window. So here's the tube window. So anywhere but there. And leakage radiation must be less than 1 milligray per hour at a distance of 1 meter from the protective housing. Secondly, we have the control panel. There must be KVP and MA indicators. There are visible or audible signals that indicate when the X-ray beam is energized. And very important, the X-ray beam must be positively and clearly indicated to the rad tech. Number three is the SID indicator must be provided. It can be tape measure or lasers, but it must be accurate to within 2% of the indicated SID. Number three is the collimation. We have to have a light localized variable aperture rectangular collimator, and the option would be cones or diaphragms. The X-ray beam and light field must coincide within 2% of the SID. PBL, which stands for positive beam limitation, is another name for automatic collimation. This is where we have automatic light localized variable aperture collimators that were required on all but special X-ray systems manufactured in the U.S. between 1974 and 1994. They're no longer a regulation, but they are often still used. PBL must be accurate to within 2% of the SID. Number six is beam alignment. Each tube should be provided with a mechanism to ensure proper alignment of the X-ray beam and the image receptor. Number seven are the NCRP Report 102 federal regulations for minimum filtration requirements. If we're operating below, a piece of equipment operates below 50 kVp, it must have at least 0.5 millimeters of aluminum equivalency. If the equipment only operates between 50 and 70 kVp, then it must have at least 1.5 millimeters aluminum equivalency. And then finally, if it operates above 70 kVp, it must have a minimum of 2.5 millimeters aluminum equivalency. Here's an image just reviewing the filtration. Filtration, as we know, hardens the beam and reduces the low energy X-rays that would have been absorbed in the patient's skin. It's comprised of inherent, which is 0.5 millimeters, and that's the oil in the glass. We have added filtration, which is 1 millimeters of aluminum, and then the mirror adds another 1 millimeter. And so for a total of 2.5 millimeters aluminum equivalency. Number 8 is reproducibility. Output intensity should be constant from one exposure to another, but the variation in X-ray intensity should not exceed 5%. An example would be if you took one exposure at 200 mA at 1 second and took the exact same exposure factors, 200 mA at 1 second, that you would expect the same results, and this is called reproducibility. Linearity is if you used a different MA station and a different time, but you have the same mass. So radiation intensity should still remain constant, but the minimum acceptable variation in linearity is 10% from one MA station to an adjacent MA station. Number 10, it must not be possible to expose an image receptor while the tech stands unprotected outside a fixed protective barrier, usually the control booth, during a radiographic procedure while they're taking the exposure. So the exposure control should be fixed to the operating console, not to a long cord. The tech can be in the room, however, but only if protective apparel is worn. Number 11 is that for mobile X-ray equipment, is that a protective apron should be assigned to each mobile X-ray unit, and the exposure switch must allow the operator to remain at least 2 meters, which is 6 feet, from the X-ray tube during the exposure. We should direct the beam away from the tech. Number 12 is the SSD, which stands for source to skin distance, the distance between the anode of the X-ray tube and the patient's skin is a minimum requirement of 30 centimeters, otherwise 12 inches. Fluoroscopic equipment. The SSD for stationary fluoroscopic equipment must not be less than 38 centimeters, which is 15 inches. And that is the distance between the X-ray tube, which is beneath the table, and the tabletop. And this just shows if we're at 40 centimeters SSD and showing that what the entrance skin exposure is compared with 20 centimeters SSD, and look how much larger the entrance skin exposure is. So we can save a lot of dose by increasing the SSD. The SSD must not be less than 30 centimeters on mobile fluoroscopic units. Number 2, the primary protective barrier, which is the fluoroscopic image receptor assembly, serves as that barrier, and it must be 2 millimeters of lead equivalency. It must be coupled with the X-ray tube and interlocked, so the fluoroscopic X-ray tube cannot be energized when the image receptor is in the part position. Number 3 is that the total filtration of the fluoroscopic X-ray beam must be at least 2.5 millimeters aluminum equivalency. And that's the same as if you are operating a radiographic unit that operates above 70 kVp. Collimation. The fluoroscopic X-ray collimators must be adjusted so that an unexposed border is visible on the image monitor when the input phosphor at the image intensifier is positioned 35 centimeters above the tabletop and the collimators are fully open. The exposure switch must be of the dead man type for fluoroscopic X-ray units, and that is if you let off the exposure switch, then the exposure ends. The Bucky slot cover is something that during fluoroscopy, the Bucky tray is moved to the end of the X-ray table, leaving an opening in the side of the table that's approximately 5 millimeters wide at the gonadal level. This opening should be covered automatically with at least 0.25 millimeters lead equivalency. The protective curtain can be a panel of at least 0.25 millimeters lead equivalency, and it should be positioned between the fluoroscopist and the patient. The cumulative timer is an audible signal when the fluoroscopic time has exceeded 5 minutes, and this ensures that we're going to alert the person who's doing the fluoroscopy, the orthopedic surgeon or the radiologist, that 5 minutes of time has lapsed. The rad tech should also record the total fluoral beam on time for each exam. The dose area product and this is looking at with no optional high-level control, the intensity must not exceed 100 milligray per minute during fluoroscopy. With optional high-level control provided, the maximum X-ray intensity is 200 milligray per minute during fluoroscopy. Design a protective barrier. So first of all, we have leakage radiation coming from the X-ray tube from anywhere but the tube window, as well as scatter coming from the patient. And we refer to that as secondary radiation. Next, we have the useful beam, which is the beam that's coming from the tube window, and it's referred to as the useful beam, otherwise called the primary beam. And if we look at our chart of lead versus concrete, 1.6 millimeters of lead is equivalent to 1/16th inch of lead, and 0.8 millimeters of lead is equivalent to 1/32nd inch of lead. You can also equate that to concrete as well. For primary barriers, these are walls or barriers to which the primary beam can be directed. It must be located perpendicular to the line of travel of the primary X-ray beam. The lead requirement is 1/16 inch or 1.6 millimeters lead equivalency. Concrete block, or brick can be used instead of lead. If the peak energy of the beam is 130 kVp, the primary protective barrier consists of 1/16 inch or 1.6 millimeters lead equivalency and extends 7 feet upward from the floor of the X-ray room when the X-ray tube is 5 to 7 feet from the wall in question. Secondary barriers are barriers that shield from secondary radiation, and they're going to include both leakage and scatter as far as those types of radiations. They should overlap the primary barrier by about 1/2 inch and must extend to the ceiling. Lead equivalencies are going to be 1/32 inch or 0.8 millimeters of lead equivalency. Gypsum board, glass, or lead acrylic can be used instead of lead. And so here's the example of the leakage radiation on the right-hand side, just showing that radiation is emitted anywhere but the tube window, and scatter radiation is emitted from the patient. For secondary barriers, the intensity of scatter radiation 1 meter from the patient is approximately 0.1% of the intensity of the useful beam at the patient. The control booth is only a secondary barrier. The X-ray tube must never be directed at the control barrier. So scatter must scatter twice before hitting the control booth. Some of the types of secondary barriers include the leaded glass window, which is typically consists of 1.5 millimeters lead equivalency. Another is the clear lead plastic secondary protective barrier. It's 30% lead by weight and shatter resistant and can extend 7 feet upward from the floor and can have lead equivalencies of 0.3 to 2 millimeters lead equivalencies. Another one is the lead mobile X-ray barrier, and I thought it might be helpful to put the lead apron next to it. The lead apron is at least 0.5 millimeters for fluoroscopy, and so is the mobile lead barriers. 0.5 millimeters lead equivalency can go up to as far as 1. Another one is the clear lead plastic overhead protective barrier, which is an open view during angiographic and interventional procedures, and it consists of 0.5 millimeters lead equivalency. So here's the opening they're talking about. There are many factors that must be considered when the required protective barrier thickness is calculated, and areas that are sent to the physicist include the distance, the occupancy, control, the workload, use factor, and KVP. So the first item is distance. This is easiest sent by sending a schematic of the room, but it's the distance of the adjacent occupied area, not to the inside of the wall of the X-ray room. The time of occupancy is the area that's being protected. So these are areas that are adjacent to X-ray rooms as suggested by the NCRP. Full occupancy areas are areas that are adjacent to the X-ray room, and they include work areas, such as offices, laboratories, shops, wards, nursing stations, those types of things. Frequent would be corridors or hallways, restrooms, and patient rooms. And occasional would be waiting rooms, stairways, unattended elevators, janitors' closets, and outside areas. The third item is control. We have controlled areas and uncontrolled areas. Controlled areas are occupied by radiology personnel and patients, where uncontrolled areas are occupied by non-occupational and public individuals. So the barrier for the control is going to be based upon the annual dose limit for the occupational worker, which is 50 millisievert. And we're going to look at the next slide to see how we calculate it, but it's 50 millisievert divided by 50 weeks, which gives us a figure of 1 millisievert per week. On the uncontrolled area, we're going to have that barrier to reduce exposure to the public to less than 0.02 millisievert per week. So how we get that is the controlled areas are based upon the annual dose limit for radiographers, which is 50 millisievert. We work a total of 50 weeks in a year, so that figure comes out to being 1 millisievert per week. When we look at the uncontrolled areas, we have 1 millisievert being the annual dose limit for the non-occupational worker, divided by 50 weeks, and we go with a value of 0.02 millisievert per week then. The workload refers to the level of radiation activity in a room. So you would calculate for the physicist specifically the MA times minutes per week that you would expect to have. A busy general purpose X-ray room may have a workload of 500 MA times minutes per week, where rooms in a private office may have workloads of less than 100 MA times minutes per week. The use factor is a percentage of time during which the X-ray beam is turned on and directed toward a particular protective barrier. The answers are going to be 0, 1/4, or a 1. So for example, the floor is given a use factor of a 1 for being a primary barrier because the X-ray beam or primary beam is directed to it a lot. Walls are given a use factor of 1/4 because they're not always used, but they're used quite a bit. Primary wall barriers in a room designated for just chest fluoroscopy are given a use factor of 1. And secondary barriers are given a use factor of 1 because leakage and scatter are present during all exams. And the ceiling is considered a secondary barrier. So looking at these use factors, we're looking at the primary barriers, use factors for the primary barrier, first of all, with the floor being a 1, the walls being 1/4, the primary wall barrier dedicated for chest radiography with no table existing in the room is a 1. The control booth and the ceiling are never primary barriers, so they're both 0 because the primary beam should never be directed at either one of them. And then as mentioned in the previous slide, all areas are secondary barriers, so the use factor would be a 1 for all of them. The final calculating item is the penetrability of the X-ray beam. And the average typically uses 75, but it might be different for a particular clinic. So all this information is sent to the physicist. So the great thing is that we don't have to calculate anything. We send this information to the physicist. They calculate to determine the barrier requirements, and rarely will the actual exposure exceed 1/10 of the dose limit. Our next topic is radiation detection and measurement. These instruments are designed to detect or to measure radiation or to do both. The measure of radiation intensity is called radiation dosimetry, and the radiation measuring devices are called radiation dosimeters. So accuracy is how correct or accurate something can be, but sensitivity is that an instrument can detect very low radiation intensities. So TLD badge and OSL are two very common badges used for both patient and personal monitoring. The TLD uses lithium fluoride and it stands for thermoluminescent dosimeter. The OSL stands for optically stimulated luminescent dosimeter and is comprised of aluminum oxide. And we'll be talking about these in a different section. The scintillation detection by operation is going to convert radiation, specifically X-rays, to light. Has many uses in the diagnostic radiology areas, but one of those is digital, where we have cesium iodide that converts X-rays to light. Gas field detectors are where electrons released are contracted to a central, which is the positive electrode, and it collects the charges. This is used to measure radiation intensity and to detect radioactive contamination. Ionization of gas is the basis for gas-filled radiation detectors. Here's that central electrode to which I was referring that's going to collect the electrons. So we have 3 of our ionization chambers: the ion chamber, the proportional counter, and the Geiger-Müller detector, otherwise called a GM counter. The ion chamber is a portable survey meter for area monitoring in X-ray, radiation therapy, and nuclear medicine. It's for things such as fluoroscopes. It's for areas around radionuclide generators. It's for areas with patients with therapeutic quantities of radioactive materials, and even outside protective barriers. The types of radiation it measures are X-ray, gamma, and beta, and it can range from 10 microgray per hour to several thousand gray per hour. It has a very wide range and it's extremely sensitive, which means it has a very low value for detection. Proportional counter is a stationary laboratory instrument. It's used to detect small quantities of radioactivity. It's useful in terms of being able to distinguish between alpha and beta radiation. And so the types of radiation it can detect are alpha and beta. That's exactly what it is. And there's no range specifically for this because it's just going to detect those radiations. The GM counter is most commonly used for area monitoring in nuclear medicine. It's used for contamination control in nuclear medicine laboratories. It's used for detecting the presence of radioactive contamination on work surfaces and also laboratory apparatus. It can detect X-ray, gamma, and beta though, and it has a range of less than 1 milligray per hour. Last but not least is talking about handling and disposal of radioactive material. One thing we're going to want to do is follow institution procedures, which means that the institution has a radiation safety program, and so you're going to follow those procedures as far as exactly what you use to do the cleanup with. Secondly, wear gloves if isotopes are in a liquid form. Third, wear a whole body and extremity dosimeters, both. Fourth, cardinal principles, always use your time, distance, and shielding, but more importantly, distance and time are very important in this case. And finally, no solid encapsulated radioactive source should ever be touched directly by hand. Long tongs adding distance should be used. And this concludes our video lesson on part 17A. Have a great day.